Hey everybody, I'm Nguyen-Tu, and this is Lab 4 of PHYS2212. The purpose of this lab is to explore the interaction between a falling magnet and a tube of aluminum foil in terms of Faraday's law that relates time-varying magnetic field to a Curly electric field. In this lab, I will be applying Newton's second law and the momentum principle. Newton's second law tells us the acceleration of an object is directly related to how much force is applied to the object. The momentum principle tells us that in an isolated system, momentum is conserved for any interaction between two objects. Incorporating these two physics principles with the velocity update formula, obtained by dividing both sides of the momentum update formula by the mass of the object, I can predict the motion of my chosen object over time. I will also be applying Faraday's law that says a magnetic flux that changes in time creates a non-equivalent Curly electric field that generates an EMF, and Lenz's law, that is the minus sign in Faraday's law, that can be summarized as nature abhors a change in flux. Lastly of note, I will also be using the general formula for the magnetic field of a dipole. To complete this lab, I'll be following three main steps. First, I'll collect observational data of a magnet falling through a conductive tube of aluminum foil. Second, I'll model the magnet-tube interaction computationally by completing the provided starter glow script code. Third, I'll compare my computational predictions with my observed data. The main result of this lab is that while the experiment had an average drop time of 1.77 seconds, the model predicted a drop time of 5.722 seconds, a 223% difference. Of note, the bar magnet had a constant velocity while inside the aluminum foil tube, while it is not near the ends. In this lab, I make three main assumptions. First, I assume the Earth's gravity and the aluminum foil tube's magnetic force are the only forces acting on the falling magnet. This means air resistance is negligible. Second, I assume the tube of aluminum foil does not move. Third, I assume the cardboard tube in the center of the aluminum foil tube, helping the aluminum keep its shape, has a negligible effect on this experiment. In this experiment, the system is the bar magnet and the surroundings of the aluminum foil tube and the Earth. The initial conditions are both the bar magnet and aluminum foil tube being motionless with velocity equal to 0. Shown here are the 5 recorded entry to exit drop times of the bar magnet down the aluminum foil tube. Shown here on the right is the model of the bar magnet falling down the aluminum foil tube with the velocity time graph on the left. Displayed here on the left is the code that details the physical constants used in the model, initializes the velocity time graph, modifies the model scene display, and creates the model key. On the right is the code that creates the aluminum foil and bar magnet with the variables for the properties of each noted under the main header. Shown here on the left are the functions used in the model, and on the right is the calculations for the forces of gravity and the magnetic force acting on the bar magnet over time. Of note, the magnetic force is calculated by first calculating the changes in flux over time for each ring that represents the aluminum foil tube to determine the induced current caused by the falling magnet that results in a magnetic force on the falling magnet. In this lab, there are three main possible sources of error. First, the magnetic dipole moment was taken from lab 2 and could be incorrect, which would affect how quickly the magnet falls down. 2. The aluminum foil tube was not held perfectly still, which could affect the direction of the magnetic force and thus how quickly the bar magnet falls down. 3. The magnet was not dropped from exactly the same position each time, which could also affect the time measurement of the magnet's drop. Comparing the model time to the actual, the model's slower time prediction suggests a greater induced current in the aluminum than what actually happened. Increasing the inner radius of the aluminum foil tube's model parameters to 2 cm from 1.5 cm, we get a time of 1.799 seconds, a 1.6% difference from the actual time of 1.77. Now for some lab questions. For one, we cannot use a ferrous tube because they contain a large enough iron content that they would attract the bar magnet and hinder its drop. For 2, the bar magnet falls at a slower rate within the tube than in free space. For 3, viewed from above, I know the red color corresponds to counterclockwise current while the blue color corresponds to clockwise current due to Lenz's law. For 4, if the magnet was flipped around, the flux would switch from increasing downwards to increasing upwards as the magnet falls down, which creates an induced magnetic field pointing down instead of up. Nonetheless, the magnetic force would still point upwards and the motion of the magnet falling down would be the same overall. For 5, as mentioned in the main result, there was a 223% difference between the model's result and the experience result. To reduce this difference and improve the model, the air resistance could be incorporated and a more accurate measure of mu mag could be chosen, since Lab 2 used a dipole approximation to calculate mu mag. For 6, the constant velocity of the bar magnet while inside the aluminum foil tube tells me that the magnet reached terminal velocity while inside the tube during that interval, with Fnet equal to 0. Reducing the resistance of the conductor by a factor of 10 increased the time the bar magnet was in the tube by a factor of 10 because the reduced resistance increases the induced current, which causes the magnetic force in the bar magnet to increase, and since the magnetic force points upward, the bar magnet falls slower. Therefore, as resistance approaches 0, causing the induced current to increase, I expect the falling magnet to fall increasingly slower to the point that it stops moving downwards entirely or even begins to move upwards. If holes or slots recurrent to the tube, I expect the ring currents in the model to be interrupted such that the magnetic force on the bar magnet is less, with some of the sideways components of the magnetic force also not being completely cancelled out, such that the bar magnet would be pushed from side to side and not fall straight downward.